Welcome, my name is Simon Ternes. I work at University of Tor Vergata on automatic controlling of perovskite solution printing, and I have the pleasure to give the webinar to you on characterization in data. So let me give a short outline of the talk. First of all, I'll introduce characterization in general, what it means, the stakeholders involved, what would be the benefits of having a living ecosystem network, and existing standardization initiatives. I'll then continue with a more theoretical part about vocabulary, workflow, and characterization, and then come to concrete examples of applied Chada, and we'll conclude with some final remarks. So, what is characterization? First of all, in a biological sense, characterization can be understood as the perception of certain stimuli by the organs that are able to perceive these external but can also be internal stimuli. In the field of material sciences, characterization is a very fundamental process to obtain data about certain material systems that are investigated. So without this characterization, progress and data acquisition could not be possible. Which methods and application domains do we distinguish in material sciences? First of all, there is a distinction between two principal kinds of characterization. First of all, there is characterization that identifies the nature of a material. So it investigates the microstructure, the chemical structure. And then there are characterization techniques that focus on the function of the material, so the performance of the fabricated device. So this is way more application oriented. For both of these classes, there can be then identified several subclasses that can also partially overlap. First of all, there is inline and offline characterization, meaning that, or answering the question if the characterization is performed during the fabrication of the material or not. We then have real-time characterization, which are techniques that are particularly suitable for inline characterization that give the feedback in a very short time without the need to process the data for a long time or analyze the data for a very long time. Then there is operando characterization, which can be applied during the operation of the device or while the function of the material is executed. And then multimodal characterization can be employed to extract several pieces of information from the material system at the same time by combining, for example, optical characterization techniques with force probing techniques. This can be achieved. So let's now ask the question, who actually performs characterization techniques? Well, these are so-called stakeholders. So in general, people that come from different sectors, be it academia, technology integrators, instrument manufacturers, and they also might have overlapping and diverging interests. So there are several subgroups of these stakeholders who all have different goals in mind. Be it, for example, the calibration of an instrument, the acquisition of data for a scientific report. And so creating or starting from these different stakeholders, different bubbles of data are created from the respective communities. So there is a need for introducing harmonization procedures and platforms that can bring together all these stakeholders, such that energy of the different bubbles of data that were created. So Chada is then, in essence, a response to having these different environments or bubbles of stakeholders, and then trying to integrate them into an open innovation environment where through communication and connection of these different services and interests that the stakeholders provide and have, a value can be created in terms of goods and services for the society. Concretely, this then manifests in data management plans, which have been decided by European policymakers to enable or describe how the data will be organized and distributed in a traceable, accessible, interoperable, reusability, and secure way. And the goal is to then create a living ecosystem of data by using more online tools for sharing information. So this ecosystem should then enable or accelerate digital innovation and technology development by also taking into account the market needs and enable machine learning on high quality data, also curate and improve the data quality and take into account the underlying fundamental material properties. So the data can then be stored according to different properties that the data has, in which time domain the data was recorded, how big the data is, and how the data is structured in terms of metadata that is available in this regard. So how can then the interoperability and the harmonization be achieved? So this is done by introducing terminology and standards. So stakeholders must find common terms with which they describe the data in terms of metadata. For this, ontologies can help, which are in essence systematic descriptions of names for specific data. And this all lies then in the framework of FAIR, which I also talked about before, which means that the data should be findable and accessible, interoperable and reusable. Who is the main actors driving these efforts? Well, first of all, there is the European Materials Characterization Council, EMCC, who brought forward a roadmap in 2017. And then there is an agreement of the European Organization for Standardization, CEN, and as a result, there is the characterization data template, CHADA, that I will detail on in the following. And so the scope of this is to coordinate and harmonize open research data by introducing these standards, finding common ground on methodologies, metadata schemes, and interfaces between material data and characterization tools, but also to foster further digitalization and automation by formulating best practices for industry and building these ecosystems that I talked about before. How Chada works is it gives the applicant of a certain characterization technique a sheet of guidelines. These guidelines are then classified according to different categories. For example, how the data is published, how it can be accessed, how the characterization was applied, so what was the workflow, and also descriptions of the sample. So in the end, by executing the guideline, the conductor of the experiment is requested to define the general terms, classify the characterization method according to the groups that I talked about before, give also guidelines how this can be translated into industry, and systematically describe the data and the applied methods. After this short introduction, let me now come to the second part concerning the vocabulary, the workflow, and classification. Now, I've talked briefly about ontologies before, but now I would like to define precisely what the term means. So an ontology is a conceptualization of phenomena in the world, and it orders these phenomena by explicitly formalizing different classes that the phenomena or objects belong to. And so the classes can have different relationships with each other, which is the so-called vocabulary. For the classification in characterization, it was performed according to the measurement probe and the signal that is analyzed, as I will detail on the next slide. Some of the classes that emerge then are mechanical analysis, chemical and structural analysis. As I told you before, the classes for characterization are created according to the probe, so the material that is brought into the vicinity of the sample to analyze it, and the response of the sample, which is then measured in the signal by a detector. So this has been formalized in the CN workshop agreement. And just to give them some examples, if we use X-ray diffraction, the probe is a beam of X-rays, and the signal consists of also a backscattered beam of X-rays. In scanning electron microscopy, we have an incident beam of electrons, and depending on the detection channel, a beam of backscattered electrons. If we have Raman spectroscopy, a beam of light is incident, and a beam of scattered light is then analyzed. In mechanical testing, the probe is a force actuator, and the resulting signal is then a displacement of this force actuator. Here you can see an extract of the class tree in the ontology. It starts with the upper class material characterization, then experimental technique, and then come the different categories of characterization equipment that I talked about before. Let's go here to the branch of material analysis, and then an indentation technique. And here the scale of the measurement is classified according to if nano indentation or micro indentation is used. And then comes the investigated material, which is in this case PMMA, silicon, and PLA. And then directly the raw metadata can be accessed of the acquired data point, leading then to the measurement files. but also material properties can be referenced, such as, for example, here, the Young's modulus or the hardness of the material. So here you can see again the same class tree in the tree view, and by putting this very rich ontology-related metadata, the data can then be traced, and experiments can also be reproduced. So there is a very good incentive in sharing data with this kind of standardized vocabulary and structure. Another important requirement in Chada is the correct specification of the workflow that was used for a certain characterization. This starts with the user case, which is essentially which kind of material was probed and what was the environment that the sample was probed in. Then comes the experimental description, which defines exactly which actions were used with the employed tool in succession, and how the probe was then engaged or activated if it's a beam, and the detector used to then detect the data. Then in the raw data step, it should be specified how the data was acquired, which data was saved, and how it was saved. And then comes the post-processing or data processing step, where it should be specified which actions the operator took to post-process the data, for example, remove noise or select certain parts of the data. This concept can then be described a little bit more in detail. So here you can see a schematic of a typical experiment. The user case would be the specimen and the medium in red. Then, depending on which routines are executed before or during the experiment, all the blue boxes here, for example, calibration, the exact equipment setup that was used, automated pre-processing, goes into the experiment category. The raw data is then obtained with the dark green box here, and then all additional methods that are used for processing after the raw data was acquired then fall into the category of data processing. So of course, what you've seen before was only for a single experiment. There can also be linked methods where different experiments are conducted as a function of the result of the last experiment. So these would be called linked methods. For example, if the output of the last experiment would influence how the next experiment will be conducted. There are, for example, also methods where the output is iteratively improved. So the post-processing of one sample is impacting the other sample and vice versa. And they can also be tightly connected experiments where 3 samples are measured simultaneously and the data is then directly put in relation to each other. This could be also, for example, multimodal methods where different aspects of the same sample are measured. So we would now like to provide you with some concrete examples how Chada is employed on a Raman laser and a nano indentation case, so that it becomes clearer how this then would manifest itself in practice. So the Chada template is structured according to 4 main points. The user case that I've talked to you before, the used method, characterization method that is characterized according to the ontology and then can also have multiple experimental steps. The validation of characterization. So here it should be described why the characterization was chosen and why it is actually containing information or is suitable for extracting information from the present sample. And the fourth point is the access conditions. So how is the sample accessed, if it was fabricated, how it was fabricated, or where it was purchased, and which is information that can be very useful for the question how the experiment can be repeated. The user case then has the subcategories of the user. So who is the person who employed the characterization technique? The sample, which kind of sample was used, what was the condition of the sample, the structure of the sample, some additional properties, so which kind of material was used, what is its chemical composition and microstructure, how the sample was handled before the experiment was started, also, if applicable, how the sample was prepared, maybe synthesized from different samples, which are the hazards, potential hazards involved in handling the sample, for example, the toxicity, and in the end, what was the environment used to characterize the sample. So was it characterized in a vacuum, in an inert atmosphere, or ambient air? The experiment part has then the following subcategories. First of all, the probe and the physics of interaction. So here it should be described how the probe interacts with the sample, so through which physical law. For example, for an absorption, it could be Lambert-Beer. Then how much of the sample actually interacts with the probe, so would be the interaction volume. How the setup is needed to be calibrated before the experiment or during the experiment to extract the data. Which detector was used, how the detector works, what the signal was that was acquired, and how the signal is structured, the measurement time, for how long the sample was measured, and other measurement parameters. So which parameters were used to then generate the signal, for example, would be integration time of the detector or amplification parameters. So quickly coming to points 3 and 4. The raw data has only 3 subcategories. The nature and format must be specified, which unit is used, so kilometers or kilograms or watts, and then the acquisition rate should also be specified, so how many data points were acquired per time. Then comes the post-processing, where it should be specified which person did the post-processing and what was their background and level of expertise, if and how the data was normalized, and how the processing can be reproduced. Is there, for example, a protocol or a number of steps in a certain software that need to be executed? If the data was filtered, how it was analyzed, for example, if it was executed, what were the signal channels that were processed, how the calibrations were applied, if calibrations were applied, which properties would also be used to analyze the data, and what was the quality of the data and how the data would be managed in the end. Now coming to the example of Raman scattering, a very basic introduction of what Raman scattering is. So in Raman scattering, there is incident light with a certain frequency, nu naught, and this light is then re-emitted from the material, and the light detected has the Raman shift that is produced by a decay not to the ground state of the material, but to one of the vibrational modes of the material. So here you can see now the complete workflow correctly specified according to JADA for the Raman measurement. First of all, a crystalline silicon reference sample is used. The sample is then positioned, the acquisition parameters are chosen, and the first calibration data is acquired. As a function of this data or the evaluation of the data, the reference sample is then repositioned and a machine calibration can be started. And in the same time, the calibration data is then used to position the thin film sample, that is the sample that should be measured for this experiment. A first measurement is conducted, and the result of the measurement is used to optimize the acquisition parameters for the very same sample, and then the final data is recorded. This data is then fed into an evaluation or post-processing pipeline where a certain numerical fit is executed, and the position of the fit, so of the fitted peaks, is then used to extract the material characteristics. Let's talk about the second example, which is nano-indentation. In this technique, a tip is driven in a very controlled way into a sample to test the material hardness and elasticity. So typically such a plot is made where the load or the force is plotted on the y-axis, and on the x-axis the displacement, so how far the tip proceeds into the sample. And you then get the loading curve, which is different from the unloading curve due to the permanent material deformation. This can also be employed then in a map if the experiment is repeated in scanning over the sample in a lot of different data points. For the nano-indentation, the workflow is then as follows. First, there is a test preparation where the recipe is selected, the input parameters are selected, and then there is a calibration and test of the locations that should be tested. This is already done on the final sample. And then using this calibration and selection of locations, the final data can be acquired. Now, from this raw data, already some material properties can be extracted that will then in the end be used for the characterized material. At the same time, however, there is a reference sample that will be tested in the exact same way. So the test locations will be selected with the same methods. And this reference data is then also post-processed and fed into the post-processing of the original sample in a way to describe exactly certain other material properties that are not directly extracted. And the final metadata then filled into the charter template for nano indentation would look like this. The colors still correspond to the 4 steps previously discussed. I will not go into detail into every of the points. Just the first is the operator is a human, and then, for example, the specimen. It is put in which kind of coating material or biomaterial is used, and in the environment, then the humidity and the atmosphere, the pressure should be recorded. For the interaction, it's then very important to specify the kind of tip that is used, how deep it penetrates, unloading steps of the tip, and so on. And the calibration, of course, then includes which kind of calibration sample will be used. So the signal is the electric current in the coil measuring the force and displacement. And yeah, the raw data will be the raw load displacement curve, and from this can then be analyzed with the post-analysis the different material properties, for example, with this Oliver Farr method, to extract the elastic modulus, the hardness, and so on. Let me conclude by some final remarks. The topic presented was mainly put forward by the European Material Characterization Council, EMCC, and the roadmap they formulated in 2017, and the CNEN workshop agreement on material characterization terminology, metadata, and classification, also formulating the charter template, characterization data template, that is very well described in the publication Innovative Data Management in Advanced Characterization Implications for Material Design by Romanos.